there, Nick here, M0NTV, and welcome back to my shack and to another video about electronics, radio building, otherwise known as homebrew. And this video follows on from the last one that I did, which was on the basics of impedance, about what it is, how you measure it, why we'd want to match it, etc. And so I've taken a few brief moments in the manic approach to Easter to do this video. Now I say this video, but actually what I'm going to do is to split this one into two parts. So this is part one. Part two is coming afterwards, and you won't have to wait very long because it will be coming hot on the tails of part one. But it was either that or just, produce some humongously big video, and I thought that's probably not that helpful. So I split it into two. So what we're going to do today is we're going to lay the foundations here for designing and building your own LC impedance matching networks, the kind of things you could put on the input or the output of an RF amplifier. And I'm going to show you the calculations. There is going to be a bit of maths, but if I can do it, I'm sure you can do it. It's not difficult. I'll step you through it. And then in part two, I'm going to show you how to cheat. and show you, because there's some great free online resources with calculators and things that help you to visualize what you're doing, which will kind of make more sense. But I wanted you first of all to kind of know how to do it properly, because for me, even when I'm cheating, I want to know what it is that I'm cheating with, if you see what I mean. I want to know the kind of basics. I don't mind taking shortcuts, but I want to know, what those shortcuts are and the kind of underlying kind of processes behind it. So I'm going to do that today. But, if you think, I'm not sure about this, hold fire, because part two should be easier. Also in part two, we'll deal with some other things as well and talk about matching complex impedances. Today I'm going to restrict our thinking about matching basically purely resistive impedances from one to another. And then we'll get onto the complex impedances next time. And the helpful cheats. So, I hope you find something of interest here, and hope you enjoy. So here we go, Impedance Matching LC Networks, a Practical Approach, Part 1. Now, we're going to be talking about so-called lossless impedance matching. Now, in reality, there's no such thing as a lossless network, because everything we build will have some inherent losses in it. But there are some forms of impedance matching that don't even try to be lossless. So they involve resistance. So I thought I'd just very briefly just cover this first before we get on to the lossless stuff. So let's assume down here, I've got my ridiculously oversized cursor as usual, we've got a source impedance here of 17 ohms and a load of 50 ohms. Well, we could match that impedance and make that source look like that load very easily by just sticking in a series 33 ohm resistor. You'd get a great impedance match. You'd get a very low SWR, but you would lose a truckload of your signal would fall and just heat up this resistor. So yes, it works, but there's a cost to that, and that cost is loss. And in case you think, well, that's a ridiculous example, who'd ever do that? Well, we do it more than you think, really. Here is a circuit that I use very often, this design, the so-called pi attenuator, because it's shaped like the Greek letter pi, with one series element and two parallel shunt elements. And this addresses that same problem. It takes a source impedance of 17 ohms and converts it to a load impedance of 50 ohms. And as I said, at the moment, when I'm talking about impedance, really I'm just talking about resistance. And yeah, you could put this in and it would do the job, but it would lose 10 dB of your power in the process. So yes, again, it works, but there's a cost to that. Now, very often when we put pi attenuators in, we're just using them as straight attenuators, but one of the things about a pi attenuator is it will do some impedance transformation, but at a cost. You know, it is lossy. So we're not going to go anywhere near resistors because, you know, we've got this hard-earned RF signal, which we don't want to waste on just heating up a resistor. You know, we want to get as much of that through into the next stage of our radio or out into our antenna as possible. But I show you these because that's one way you can do it. So what about lossless impedance matching? Well, again, this is a huge area and probably one of the most well-known examples of lossless impedance matching is all kinds of different transformers and transmission lines. And there's just a couple of examples shown down there. And to be honest, up until fairly recently, virtually all of my efforts to match impedances will be these. I will build different flavours of transformers. And they can work very well. Again, of course, although they're meant to be lossless, they're not. And the funny thing, you know, even when you build a transformer like this, which will obviously have inductance and will display a large inductive reactance, you'll also get stray capacitance because all these little windings act as little capacitors. So you end up with more than you kind of bargain for. Anyway, so this is a whole topic on its own. I'm not going to cover this. I have touched on how you calculate and build impedance matching transformers before. Probably I think the best example, if you're interested, is in my video Crystal Filters for the Fearful, because I build matching impedance matching transformers on the in and the out of my crystal filters. So go and check that one out if you're interested, and at some stage I'll probably need to do a video just on these. But we're not looking at those today, we're looking at something different. What we're going to restrict ourselves to looking at is actually to this LC matching networks. Now, this can be a bit confusing because in a minute I'm going to start talking about L matches, and I mean a different thing here. When I'm talking about LC matching, I mean L for impedance and C for capacitance. So this is where we use the reactive nature of inductors and capacitors to effectively change one impedance to make it look like another. And this is the amazing thing that we can do with reactance. And as we looked at in the last video, inductors have inductive reactance and capacitors have capacitive reactance, and we can use these two to transform impedance. Okay, there are different ways of doing this. Different combinations of inductors and capacitors that we can use. And I'm just going to show you a few of these. So one is the so-called pi match. Now we've just looked at a resistive pi attenuator, so the shape will be familiar. Incidentally, the names of all these are based on their physical appearance on a schematic. So it's called a pi match because it looks like the Greek letter pi. And so it consists of one series reactive element, could be a capacitor, could be an inductor, and then two parallel shunts, and that's a pi match. Closely related to that is the T match. No prizes for guessing why, because it looks like a capital letter T, and again that's just got one central parallel shunt and two series reactive elements to it. But we're not going to think about either of those. We're going to keep it as simple as it gets. We're going to concentrate on the humble L match, and this consists of just two reactive components. Now, the reason it's called L is not here because L for inductance. It's L just because it looks like a capital letter L, or admittedly on its side, it's here. And that's all an L match is. It's just two components. So usually an inductor and a capacitor, either way round. But it could be two inductors, could be two capacitors. And actually, there are 8 different permutations, would you believe, of how you can arrange an L match. And so what you can do is you can have a series inductor and a parallel capacitor, or you could swap those around. You could have a series capacitor and a parallel inductor. Now, what you could also do, if you look at this one here and compare it to this one here, you could change where this parallel capacitor comes. So on this one, the parallel capacitor comes after the end of the inductor. On this one, it's at the beginning. And that makes a big difference as well. I'll talk about that in a moment. And the same for this one, where we've got a series capacitor and a parallel inductor. The inductor's at the end there, but it's at the beginning here. And you can do the same with just the same components. So two capacitors, one with a shunt at the end, one with a shunt at the beginning. Two inductors, one with a shunt at the end, one with a shunt at the beginning. Now, it's these top 4 that we're going to be mostly thinking about. And there's 2 important things to say about the way these are arranged. The first is this business of whether your shunt component, your parallel component, comes at the end or at the beginning of your series one. And here's the thing. The shunt component, the parallel component, whether it's an inductor or a capacitor, needs to go on the end with the highest impedance. Okay? So the shunt end, the parallel component, needs to be on the side, there's two ends here, the front and the back. So on this back end of the inductor here, this needs to be the element with the largest impedance, and this is the smaller impedance. So we can see here clearly that in this L match the larger impedance is this end. We can see here the larger impedance is this end. Now these two, we can see actually the larger impedance is at the front and the smaller impedance is at the back, and the same for this one. So that's the first thing. The second thing is, it makes a big difference whether you have an inductor as your series component or a capacitor as your series component. Because if you've got an inductor as your series component and then you've got this shunt to ground with a capacitor, that actually, and if you think about what we talked about in the last video about the way reactance works in inductors and capacitors, and think about, we talked about inductors could be used as RF chokes to choke off high frequency. This functions as a low pass filter, because this will attenuate high frequencies but will pass low frequencies, and the capacitor will let the high frequencies go to ground. So this is a low pass filter with an inductor in series and a capacitor to ground, and this is a low pass filter. The only difference with this and this is a low pass filter where the higher impedance is this end, and this is a low pass filter when the higher impedance is this end. So you won't be surprised then to know that this design and this design are in fact high pass filters. So here's your capacitor, which will allow the high frequencies to pass through relatively unattenuated, and here, shunting to ground the lower frequencies, is the inductor. So this is a high pass, and just the same, a high pass with a larger impedance this end, a high pass with a larger impedance this end. Now, a wise person once said, there's no such thing as a free lunch. And whilst these two components are able to match most impedances, with just two components, which is pretty impressive, there is no such thing as a free lunch, and there's a fair degree of compromise. Now, it's my contention that there are three main factors which govern impedance matching networks. Now, technically, I think we could argue there are four, because one of them is loss. But we've already talked about loss, and so because we're not using any lossy components like resistors in our networks, we're going to put loss to one side. But there are three main factors, I think, which govern the way that our matching networks will operate. And the truth is, every network is a compromise between these three competing factors. Each of them wants to be the most important thing, but they can't all be, right? And you can't have it all, I'm afraid, because you will find that optimizing one is fine, but will mean you have to accept less performance from another. So what are these three competing factors then? Well, the first one is what I would call the impedance matching ratio. We're going to look at all these in a bit more detail in a moment. So this is just the amount of ground that we're trying to cover. So how widely spaced apart are these impedances that we want to match, right? That's the ratio. The second is the impedance matching bandwidth. So over what span of frequency do we want this match to be effective? And thirdly, the network complexity. Just how complex do you want this thing to be? Because you've got to build it after you've designed it at the end of the day. And we're just going to briefly look at each of these. So let's take the impedance matching ratio first of all. So the question we ask is, what is the ratio of the impedance values that you're trying to match? Now, down on the left here, this is it's a LT Spice screen grab of a design that comes from Experimental Methods in RF Design, and it's a Wes Haywood design, I think, for an RF pre-driver. It uses a single 2N3866 BJT transistor. And now, on this instance, he used a transformer to do the matching. We're not going to worry about that now. And look, there's a pi attenuator here as well. But the actual load is 50 ohms. But what I want you to note here is that the impedance at the collector, as is the case for many common emitter amplifiers of this kind of design, is about 200 ohms. So we've got 200 ohms on the collector, and we've got 50 ohms in the load. Well, that is actually a 4-to-1 ratio. 4-to-1, 200 down to 50. Let me show you another one. Now, this comes from a data sheet of a power BJT transistor, which will remain nameless for now. I mean, just note, actually, as is very often in data sheets, they don't even put a transformer in for the matching networks. They put LC matching networks. There's one on the output here, and there's one on the input. But what I want you to note here is that actually the impedance at the base of this transistor is incredibly low. It's actually less than 2 ohms. But the RF input signal that's coming in from our other transmit amplifiers is 50 ohms. So we've got to step it down from 50 ohms here to 2 ohms here. Now you might think, well, that's easy enough, isn't it? We've just stepped it down from 200 to 50. But 200 down to 50 is a 4-to-1 matching ratio. 50 down to 2 is 25-to-1. That is a big ask a very big ask. And as you'll see in a minute, you can do it. But if you're going to max out the impedance matching ratio, then there will be a cost to these other factors that we're going to look at. There's no such thing as a free lunch. It's all about compromise and what compromise you're prepared to accept in each of these three categories. So that's the impedance matching ratio. Well, what about the bandwidth? So here's the question. Over what frequency span do you want the impedance match to be effective? You might think, well, what do you mean by that? Well, what I mean is there's good news and bad news. So the good news is, as I've said before, most impedances, believe it or not, can be matched using just two components in an L-match network. Amazing when you think about it. Just two components, you can match most impedances. But the bad news is this match will only be at one particular frequency. Now, if you're building a tuned amplifier, or your amplifier is in an IF section perhaps, where you've only got a signal at one particular frequency, that's perhaps no biggie. But if you're, as I am doing, putting a matching network on the input of a more wideband RF amplifier, then that is a big deal. Because you think, well, hang on a minute, I want it to be as wide as possible. But here's the thing, you see, this shouldn't surprise us, because what are we doing here? We're using the reactive properties of inductors and capacitors to do this impedance matching for us. But reactance, as we learnt very clearly in the last video, is highly dependent upon frequency. And that makes a big difference. Let me just show you. Now, the bandwidth is closely related to the loaded Q. Now, I don't really want to get stuck into Q. Q is enormously confusing, I find, mainly because there are at least three different definitions of what Q is. We can talk about unloaded Q, which largely is confined to individual components. We can talk about a capacitor or a crystal in a crystal filter, and is a measure really of how effectively they use the energy which comes through them. So in a capacitor it would be, the reactance over the equivalent series resistance. The loaded Q is a bit more easy to kind of define. Now, loaded Q really applies to resonant circuits, and it's really a measure of how the bandwidth is very dependent upon the centre frequency. So the actual formula is here. So the loaded Q is the frequency divided by the minus 3 dB bandwidth. So this is, when you think about the bandwidth, where the signal level drops to minus 3 dB before and after the centre frequency. And just incidentally, the third Q is what they call Q of the load, which is where you're looking at a kind of whole kind of circuit as one, as it were. But just thinking about this for a moment, you get an idea about what I'm talking about here. Because let's keep the math simple. Let's say we were at 100 megahertz, and we had a loaded Q of 10. So you can rearrange this easily enough. So the minus 3 dB bandwidth would be 100 divided by 10, which is 10. So at 100 megahertz, a Q of 10 will give us a bandwidth of 10 megs. Great, happy days. But if we were to drop down to 10 megahertz with a Q still of 10, that would only give us a bandwidth of 1 megahertz. And if we were to drop down another factor of 10 to 1 megahertz with a Q of 10, our bandwidth now would only be 100 kilohertz. So you can see the massive effect that the centre frequency has on the bandwidth that we're trying to get. So for our point of view, generally speaking, a lower Q is what we want, because a lower Q means a wider bandwidth. And finally, the complexity of the network depends very much on these two factors I've just spoken about. Because if you want to have a high matching ratio, like I spoke of, like going from 50 down to 2, and if you also want a wide bandwidth, then you're going to end up with one complex network. And the truth is that even if you make this complex network as complex as it can be, and you do reach a point actually where additional complexity doesn't actually result in any substantial gain. There's a kind of threshold after which it gets more and more complex for less and less kind of results. You might find that you just can't do it. You can't have everything you want, and you might just have to settle for either not having such a wide bandwidth, or you might have to settle for not being able to match the impedance differences that you want to. Now, there are some ways around this, and in the next video I'll talk a little bit about it. What you can do is, instead of saying, well, all right, maybe we can't go down to 50 to 2, maybe we could break that up and have, as it were, some kind of intermediate kind of virtual resistances that we're going to match to, and kind of stack some L match networks in series one after the other. And you can do that and break it down, which will give you a lower Q and will give you a wider bandwidth. So but of course it greatly increases the complexity. So you see what I mean? So the real challenge here is to actually decide, well, what's actually going to be doable in reality, because designing it is one thing, building it and getting it to work is something else. So it is a compromise, but it can be done, and it can be, if you can get it right, it can be done very effectively. Okay, how you doing? Are you still with me? Okay, brace yourself for the next section. You might want to go and make yourself a strong cup of coffee. Other beverages are available. And we're going to dig in to designing our first L-match network. So here we go. So we start, of course, with a source and a load. And the first question we need to ask ourselves is, which one has the smaller impedance? And as I said, really what we're talking about at the moment is which one has the smallest resistance. So whichever one it is, and it doesn't matter whether it's the source or the load, whichever one I would suggest you refer to as R1. So whichever one is the smaller, call it R1. And whichever one is the larger, call it R2. Now, the next thing, once you've assigned which one is larger or which one is smaller, is to think what we're going to do. What we're going to do is we're going to use series and parallel reactance to make R1 look like R2. So, in order to do this, if we're going to use series and parallel reactance to do this, then we need to calculate what series and parallel reactance we require. So that's what we're going to do next. Now, don't be upset by these formulas. They're not that bad, really. So you'll see here. Now, you need to start with series, because series reactance is XS, and you'll see that in order to calculate parallel reactance, you need that value of XS. So we all start with the series reactance. So the series reactance is the square root of R1 times R2 minus R1 squared. And that will give us our series reactance. The parallel reactance, XP, is R1 squared plus XS, the series reactance, squared over XS. And then we can also calculate Q, and there's a separate formula for this. So the Q of our L match will be the square root of R2 over R1 minus 1. Now, we're going to do a worked example so you can see this. And actually, this example comes from the hallowed pages of experimental methods in RF design. This is one of the examples that they use. So let's imagine we have a source impedance of 10 ohms and we want to match that to a 50 ohm load. So I guess this would be like if you had an output port of an amplifier that had a very low impedance, like 10 ohms, and you were trying to match it to the 50 ohms load. You can view these either way around. So what I mean is, when we built this, the 50 ohm load, as it were, looks into what we're going to build and we'll see 50 ohms, right? The 10 ohm source, or 10 ohm end, will look in and we'll see 10 ohms, right? So they work both ways. So we've got 10 ohm source, we've got 50 ohm load, we've got 7 megahertz signal. So we ask the question, which one has the smaller impedance or resistance? Well, clearly that's our source, so we're going to label that R1, the smaller one. And so we're going to label the load R2, which is the larger one. And then we just plug the numbers in. So the series reactance then will be the square root of the source, 10, times the load, 50, minus the source squared, 10 squared. That comes out to 20 ohms. The parallel reactance, if you plug the numbers in, gives us 25 ohms. And the Q, if you do the maths there, gives us 2. So we require, to do this transformation from 10 ohms to 50 ohms, we require a series reactance of 20 ohms and a parallel reactance of 25 ohms. And we'll do that with a Q of 2. So let's have a look at it then. So I put those values up here. So the series reactance 20 ohms, the parallel reactance 25 ohms. So the next question we need to ask is, what form of L match do we want to use? Do we want to use the low pass version or the high pass version? Now, as I said, at the frequency in question, so at 7 megahertz, the center frequency, it'll look identical. There will be no difference, right? But as you move away from the center frequency, you will see a difference. And not surprisingly, if you choose the low pass topology, then you'll get a much better impedance match on the frequencies below. But if you were to choose the high pass topology, you would actually find that, yeah, 7 looks good, but the frequencies above 7 seem to be a lot better. So it just depends on what your use case is. We're actually going to do them both, so you can see, but we're going to concentrate mainly, first of all, on the low pass, but I will show you what the high pass looks like as well. So, okay, let's do a worked example then of a low pass. So here it is, I put it in. So you will remember that the low pass is a series inductor and a parallel capacitor. And hopefully you'll also remember what I said about where this shunt reactive element goes on, where the largest impedance is. And because R2 is here, because this is the larger one, 50 ohms, so that's where this one goes. If you put this capacitor on this side, it would not work, right? So that's really important. As I said, it works both ways in terms of, looking in that way, it'll work. Looking in that way, it'll work, but not if you get this capacitor in the wrong place. So that's really important. So that's what we do there. And let's just put these values in. So we calculated that we needed a series reactance of 20 ohms. But now, look, because we've gone for a low pass option, we know that our series component will be an inductor. So it won't just be a series reactance of 20 ohms we need, it will be a series inductive reactance of 20 ohms. And the same for our capacitor. We calculated that we would need 25 ohms of parallel reactance, and because it's a capacitor that is our parallel component, it will mean it will be 25 ohms of parallel capacitive reactance. So let's start with the inductor. So we know now that we need 20 ohms of inductive reactance. So all we've got to do is dredge up those formulas I showed you in the last video for calculating reactance. So just rearranging the one for inductive reactance gives us this. So if we want to find out what value that inductor should be, it's L, the inductance, is the reactance, the inductive reactance, which is our series reactance, 20 ohms, over 2 pi times the centre frequency, 7. So if we plug that in, that gives us L equals 20 over 2 pi, 7 times 10 to the power of 6, so 7 million if you like. And when you calculate that, that gives us an inductance of 455 nanohenries. 455 nanohenries, and we'll put that there. And now we just do exactly the same with the capacitance. But because it is capacitance, which is our parallel reactor, we need to use the formula for capacitive reactance. So that's this. If we rearrange this, so the value of this capacitor will be 1 over 2 pi f, 7 megahertz, times xc. So that is the capacitive reactance, and because it's in parallel, it's xp. It's our parallel reactance. So let's plug those numbers in. So that gives us 1 over 2 pi, 7 times 10 to the 6 times 25, this value here. And when you calculate that, you get a capacitance of 909 picofarads. So we put that in. And that's it. If you do that and you build that, it will work. It will take this 10 ohms and match it to the 50 ohms load. And just for the sake of completeness, let me show you the high pass, and I've already calculated this out, but it's exactly the same. The only thing you need to remember, of course, is that these values are the same. You know, we've still got 20 ohms of series reactance, and we've still got 25 ohms of parallel reactance, but now, because we're in high pass topology, that means that instead of an inductor here, we've got a capacitor here. So we need to use the capacitive reactance formula this time for this one, and we need to use the inductive reactance formula for this one. Okay, so that's why we've got different values here. 1.14 nanofarads for the capacitor and 568 nanohenries for the inductor. And again, that will work as well. Well, I'm sure you don't just want to take my word for it that it works. So in part 2, we're going to do a few things. Firstly, I'm going to show you this working, and you'll see a simulation of it working visually. Secondly, I'm going to show you how to cheat. Way, and that's pretty cool actually, using some great online resources and simulations and calculators that will help to simplify this process and help you actually see the effects of these calculations that we've been doing today. Then I'm going to show you how you can actually match complex impedances, so not just purely resistive ones that we've been doing today. And finally, just to show you what it looks like when you put one of these L networks on a real life amplifier and the difference that it makes. So that's all for next time. In the meantime, Thank you ever so much for watching. Please like and subscribe. But do have a very, very happy Easter, and I will catch you in part 2. Thank you. 73. Bye-bye.